Students, some more clarifications related to Nyquist criterion I want to give, because when I explained about the theory of Nyquist criterion, I told that time that you will get a better idea when you are doing the problem. So what I am going to do is I will show the relationship between that and problem. Thank you. So here what I will do is so here when you are coming to the Nyquist, the mapping of the Nyquist contour into the Nyquist contour to the Nyquist contour to the Nyquist spot is carried out as follows. So here limit of s tending to r into e to the power of j pi, that is r is tending to infinity, g of s into h of s is equal to real constant, and one condition inside the bracket, it is 0 if m is less than n. M is less than n means number of 0 is less than number of pole. That means number of numerator component is less than number of denominator component, and it is real constant when m is equal to n. Number of pole is equal to number of zeros. So when you are coming to our example, you can see that here g of s into h of s is equal to s plus 4 divided by s plus 1 and s minus 1. Here 1 0 and 2 poles. So number of zeros is less than number of poles. In that case, in our problem, we observed that limit r tending to infinity, r into e to the power of j pi plus 4 divided by r into this same expressions, limit r tending to infinity, g of s into h of s is equal to, you are getting the value as the same expression, the value as 0, magnitude is 0 with the e to the power of minus j pi. So this I want to clarify. So that is the contour C2. This is related to the C2. It is 0 if m less than n. That means number of 0 is less than number of poles. Yeah. Then open loop poles in a j omega axis. So here, if the open loop transfer functions g of s h of s and therefore the characteristics polynomial 1 plus g of s h of s has any poles on the j omega axis, the Nyquist contour defined earlier, this one defined earlier, this is the Nyquist contour defined earlier on S plane. Yeah, Nyquist contour defined earlier, Nyquist contour defined earlier cannot be used as such, since the S-plane contour should not pass through a singularity of 1 plus g of s into h of s. We already studied that what is a singular point. The first, yeah. So here you can see that for every point s in the S-plane at which q of s is analytic, then only you can do the Nyquist criterion. A function q of s is said to be analytic in the S-plane provided the function and all its derivative exist. The points in the S-plane where the function or its derivative does not exist are called the singular points. So the pole of a function are singular point. So pole of a function are singular points. So the contour should not pass through a pole. So that is why if there is a pole on the JM axis, you cannot have the Nyquist contour through that. So what you can do is, in such cases, this to investigate stability of in such cases, the Nyquist contour must be modified so as to bypass any j omega axis poles. This is achieved by indenting the Nyquist contour around the j omega axis poles along a semicircle of radius epsilon, where epsilon tending to 0 as shown in figure. So here, this is the new Nyquist contour. As you can see that wherever there is a pole on the j omega axis, the contour bypasses that, and the radius of that is represented by epsilon e to the power of j theta, that is the arc representations, and epsilon tending to 0. And at this point, the arc is represented by j omega 1 plus epsilon e to the power of j theta. If the poles are at origin, then it is e to the power of epsilon into e to the power of j theta. So C2 is same as previous, but C1, wherever the pole exists, there you should bypass.